Today we will discuss about design and implementation of dielectric resonator antennas for energy harvesting applications. We will talk in specific to 5G and 6G applications. You are already aware that generally we find metallic conventional antennas. Today we have come up with another type of antennas, that is dielectric resonator antenna. These antenna has advantage over metallic antennas. Reason being, they use dielectric material for resonating, and these are having three-dimensional features. They will be able to excite not only a fundamental mode but higher order modes. And the application of higher order modes are that if we can excite higher order mode in addition to fundamental mode, we can play with these resonant modes to create multiple resonances, to create mode merging effect, to generate ultra wide band. And the specific application of these dielectric resonator antennas which are being developed for sub 6 gigahertz as well as at terahertz frequency will be useful for 5G and 6G applications. How, we will see in detail. Now, if we see in this first slide, the main topic of presentation will be the design and implementation of ceramic based dielectric resonator antennas. Here we will talk in specific to the hardware development, simulation as well as the mathematical analysis of DRS. Resonance, modes and DRA excitation will be the few features. Generation, resonance mode control and higher gain along with higher bandwidth will be the few parameters. Beam width, antenna gain, bandwidth, DRA shape, these will be the crucial points to discuss in this particular lecture. DRA with circular polarization is another advantage. We can have frequency shift control, bandwidth control, resonant mode control, radiation and beam control, device miniaturization and deminiaturization control. All these features can be achieved in the DRA designs. DRA stands for dielectric resonator antennas at microwave frequency as well as at terahertz frequency. So in sub 6 in 5G we are having different bands like sub 6 gigahertz to 77 gigahertz, 95 gigahertz. These are millimetric wave bands which are very useful for lidar, radar and different 5G communication applications. Beyond 95 gigahertz we have some specific terahertz frequency where we can design very compact antennas or compact DRAs. Now, why we should go for terahertz or millimetric wave band? We are already aware that the speed of 5G communication can lead us up to 10 Gbps, or if further we can extend, it can go beyond 20 Gbps. But if we talk about terahertz or 6G communication, the speed of communication will be in terahertz. So in place in 100 Gbps or 2-3 tera Tbps. So that is huge speed. There are few European countries and US which are working in this 6G, and Europe has already implemented 5G communication bands. So they are able to get their speed up to 20 Gbps in case of 5G, and up to 3 Tbps will be the speed of 6G communication. So huge advantage is there. Now coming back to our today's topic, why DRA? This is a crucial parameter. We have ceramic material, we have stable operation, we have high dielectric constant, we have high efficiency, we have lower losses, we have size miniaturization technique. The time varying, the basic phenomena of DRA is that the ceramic or dielectric material will resonate at particular frequency, and the resonant frequency will be depending on the dimensions, input excitation, and there are other coupling techniques on which these mode of operation will depend on. Now, this is basic building block of 5G DRA. Here we can see there is a block which is rectangular in nature, has a particular permittivity epsilon r, it has the particular height, it has width and length. So, there is a k, the wave vector, and the angle theta will decide at which point of operation we want to transmit our energy. Now, in this DRA, we will see that there are three types of fields which we can excite. One is far field, another is near field, and inductive field. So all these three types of fields has different applications, but generally for 5G and 6G communication, we make use of far field operations. Now, here is basic of DRA, but I want to discuss more specific as far as the design and application of 5G, that is sub 6 gigahertz, and 6G, that is terahertz frequency. The basic objective to select the dielectric resonators is that we will be able to excite not only fundamental mode but higher order modes. And these modes we will be able to play with. We can shift these resonant modes to our desired operation. We can merge these modes for wider band application. We can split these resonant modes for independent band applications such as Wi-Fi, GPS, WiMAX, and many other satellite or other communication techniques are concerned. So, depending on the requirement of 5G and 6G, we will be able to design our DRA to operate for any particular frequency. There is one more application of DRA, being very huge amount of gain. We want to use these gains for generation of radio frequency energy. How? We have identified one field of operation as in specific 4G, 5G and 6G. There are drones, they have battery life. So if we can work with the point that battery life can be extended for certain duration of time, maybe half an hour, maybe 1 hour. So we want to use this dielectric resonator antennas to generate radio frequency energy, and this radio frequency energy will be able to extend life of drone flying hours. How? That we will see in the coming up slides, that the DRA will be able to receive can be designed for particular frequency, or it can be designed to receive multiple frequencies, and these multiple frequency bands can be integrated with the rectifier circuit, and these rectifier circuit will be able to convert the RF received energy into corresponding DC voltage. The DC voltage, of course, till now we are getting very less DC voltage, but there are few techniques by which we will be able to multiply the received DC voltage, or there are few techniques by which we can receive multiple bands from the same DRA, and these multiple bands can be combined through combining network, and this combining network can be given to a rectifier circuit. The rectifier circuit are again of two different types. One is based on Schottky diode, another is based on CMOS rectifier, that is new coming up technology. And in CMOS rectifier, the power conversion efficiency is very huge. So the third technique is that we can integrate the Schottky diode rectifier in combination or in amalgamation with the CMOS rectifier, so that the Schottky diode will be able to give us higher voltage, and CMOS rectifier circuit will be able to rectify lower voltage, and then we can integrate higher voltage Schottky diodes and low voltage CMOS rectifier circuit into one combined. Thus we can get higher DC voltages by adopting this type of configurations. So there are 3-4 milestones being achieved in this type of configuration. One is that the DRA or combination DRA or metallic structure will be able to offer us higher gain or higher received gain. With that, we will be able to receive higher input power, and this higher input power will be on multiple bands, where we can use combined effect of the received power. Thus huge amount of received power amplification will take place, and then this amplified received voltage will be further given for the rectification, so that PC, the power conversion efficiency, get enhanced. In that, we target that we will be able to use the Schottky diode rectifier in combination with CMOS rectifier, so that we are able to achieve lower voltages as well as higher voltages, and that combined effect will generate us huge amount of DC voltage, which can be used for IoT devices, or such as the drone, where the drone battery life can be extended. So this is a use case where the flying time of drone can be enhanced by using radio frequency energy harvesting. There are other applications such as the implants. The implants are generally supplied with the battery. So these implants, if can be supplied with the RF energy, then the battery life can also be enhanced. There are some other healthcare applications where sensors are there, where these smart homes are there, where DC homes are there, where smart city is there. So these type of devices will be generally on low voltage DC, so they can get the extended life of operation. Or sometime, if we see recently, the Samsung has developed a remote. This remote is based on without any, there is no cell, only the in-house Wi-Fi is able to supply to this remote, and no pencil cell is required in that remote. So this type of device can be the huge amount of life, or life without, they can operate without any battery. So in my conclusion, I will say that the radio frequency energy harvesting is very helpful if these low power IoT devices are there. No battery, no power supply will be required. They can be directly be operated at radio frequency being received. With this, I conclude my 2Z Life. Thank you.